All right, y'all. Today we're going to be talking about matrices and matrix operations. Now, matrices is something you may or may not have seen before in mathematics, and it might seem like a bit of a weird deviation from what we've been doing with systems, but it's actually going to be really important to how we solve some of those more complex 2x2 and 3x3 systems. We're going to kind of utilize some matrices. But before we can get to that more advanced skill, we're going to start with kind of the basic, what is a matrix or matrices, and how we can use them, how we can work with them. Okay, so there's two really important pieces of vocabulary we're going to work on today. The first part is a matrix. A matrix is a rectangular array of numbers written within brackets. So you'll recognize a matrix when they have these sets of numbers written in between two big and large brackets. And then within any matrix, we have matrix elements. And matrix elements are just any specific element in that matrix. So we always identify our matrices by their rows and columns. So it's always rows and then columns. So in this case, we have 3 rows, -5, 2 is a row, 0, -1 is a row, -9, -2 is a row, and then 2 columns. And so it's a 3x2 matrix. We also tag any matrix element, row, then column. So like looking at our matrix A, if I'm looking at this element 8 right here, it would be matrix A, element 2, and then 3. So A underscore 23 would refer to row 2, column 3, and that would, of course, give us that element 8. Okay, so that's kind of some basic, what is a matrix? How do we kind of identify it? Let's apply some of these skills, though. Okay, so let's look at number 1. We want to write the dimensions of each matrix below. So we have -1, 5, 0, -6, and 3, -3, 8, and 2. So we can clearly see right here that we have 2 rows. And then down on across, we have 1, 2, 3, 4 of our columns. And remember, it is always rows by columns. So this would be equal to a 2x4. Pretty straightforward. If you want to pause, you can for number 2, or you can just do number 2 with me real quick. So number 2, we notice right off the bat, we only have this one row. And then once again, we do have those 4 distinct numbers. So that's going to represent those 4 columns. So this would be a 1x4 matrix. And relatively straightforward. Okay, now once we kind of identify how we can actually look at matrices, we can actually do some operations. And the first one is probably the most basic. It's matrix addition and subtraction. To add 2 matrices, they have to be the same size. So they have to be, same rows, same columns. And then it's really straightforward. If we're adding 2 matrices together, we just add all of the corresponding elements to each other. So A11 would add to B11, A12, B12, A21 to B21, A22 to B22, and vice versa if we were doing subtraction. So it really is relatively straightforward. So like if I'm adding and subtracting 2 matrices, C and D, I'm just adding all 6 of those elements, same corresponding element together. C minus D, same thing. I'm adding each of those elements together. So let's look at an example. Let's subtract these 2 matrices. The matrices 1, -2, 0, -6, and 6, -3, -1, and -8. So if I'm going to be subtracting these 2 matrices, then I'm going to take each element and I'm going to write the first element in my matrix A first. So each one I'm going to do 1, -2, 0, and -6. And I'm going to be subtracting everything in that second matrix. So minus, 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 minus. And then, of course, this second matrix. So 1 minus 6, -2 minus -3, 0 minus -1, and -6 minus -8. Okay, so it's just all of those same exact terms in the exact spots that are being subtracted from each other. Now, of course, if I do have any double negatives, I want to go ahead and change those to be addition signs. So this is going to be an addition, that's going to be an addition, and that's going to be an addition. And then I can simplify this matrices. So 1 minus 6 would be equal to negative 5. Negative 2 plus 3 would be equal to 1. 0 plus 1 would be equal to 1. And negative 6 plus 8 would be equal to 2. And it's really as simple as that, y'all. When we're doing matrix addition or subtraction, you're just adding or subtracting each of those terms to the exact same corresponding term. So go ahead and pause me and try the second one over here. This one is addition, and I'll go over it in just a moment. And just like our last one, y'all, we're just adding each of those terms together. So negative 9 plus negative 7, 2 plus negative 3, 0 plus negative 4, negative 1 plus 8, 0 plus negative 7, and 3 plus negative 9. Of course, it's addition, so we don't have to worry about those double negatives. So I'm just adding each of those terms together, and we get negative 16, negative 1, negative 4, and 7, negative 6. And remember, addition or subtraction, they have to be the two same size matrices, and our solution is, of course, also going to be that same size of matrices. All right, so let's pivot, do something a little bit different. The next one we're going to do is scalar multiplication. So when I talk about scalar multiplication, I'm talking about multiplying a matrix by a number. I'm multiplying that matrix by some constant on the outside, so by 2, by 4, by negative 3, something of that nature. And it's really straightforward. If I multiply a matrix by a scalar, I just multiply every single term inside of that matrix by that scalar. So if I have matrix A and matrix B, and I wanted to find 4A plus 3B, the first thing I would do is I would multiply every single term inside of each of those matrices by that scalar. So 4A would be 4 times the matrix A. 4 times 2 is 8. 4 times 8, 32. 4 negative 3, negative 12. 4 times negative 1, negative 4. 4 times 5, 20. And 4 times 2, 8. So I'm just multiplying every single term by that scalar. Same thing on that other one. And then once I've multiplied and found both of those new matrices, I can, of course, complete any addition or subtraction if I need to do a little bit extra. Okay, so let's look at this example here. What is 2a plus 4d? Okay, so 2a and 4d, that's going to be 2 times a first. So 2a is going to be equal to just every single one of these multiplied by 2. So 2 times 1, and then 2 times negative 1, 2 times 3, and 2 times negative 2, which of course would give me the new matrix 2, negative 2, 6, negative 4. Ooh, of course, not a parentheses. I want to use those brackets. So relatively straightforward, just like addition and subtraction, y'all. Kind of almost works out how you'd probably think it should. So same thing. I'm doing 2a and then 4d. So 4 times d would be equal to 4 times 1, 4 times 0, 4 times 0, and 4 times 1, which would equal 4, 0, 0, and 4. And once again, I get my brackets and my parentheses mixed up. All right, and then last but not least, we are adding them. Go ahead and pause me, y'all, if you want to do that one on your own, or you can follow along with me if you want to actually add these together. Still see me doing it. So we're going to take those two matrices. So 2 plus 4, negative 2 plus 0, 6 plus 0, and negative 4 plus 4. And that would, of course, equal the new matrix. 2 plus 4 is 6. Negative 2 plus 0 is negative 2. 6 plus 0 is 6. Negative 4 plus 4 is 0. And so we get that simplified matrix. So we can combine some of these operations together. Scalar multiplication, of course, could just happen on its own, or we can do it with matrix addition or matrix subtraction. Okay. Now, really the more advanced skill, and this is what we're kind of trying to build up to, is what we actually call the product of matrices. And to be able to take the product of matrices, we have to have a few kind of different rules. So with our scalar multiplication, addition, subtraction, we just want to have matrices that are the exact same size. So same set of rows, same set of columns. So 2 by 2, 2 by 2, 2 by 3, 2 by 3. In the case of our examples, 2 by 3s, 2 by 3s, 2 by 2, 2 by 2s. So same exact thing for addition, subtraction, and scalar multiplication. For products, we actually want to have something kind of wonky. We want to have the same amount of columns in the first matrix as rows in the second matrix. And then the rows of the first matrix and the columns of the second matrix is going to be what actually creates that product matrix. It's going to be that size. So it's a little wonky to think about, but essentially what happens is I need to have those equal number of columns in the first one and rows in the second one to actually do my multiplication across. And you'll see it when we kind of put it into action here in a little bit. Okay, but with a lot of times with doing products, y'all, it's not just doing the actual product, it's just determining, can I actually take it? So looking at these two products, if I wanted to do A times B, and I know usually multiplication wouldn't be important, but with matrices, order for multiplication is important. So A times B would be my 3 by 2 matrix in matrix A times my 2 by 4 matrix in matrix B. Note how the 2, which is the columns in matrix A, and the 2, which is the rows in column B, are the same, which means my answer would be a 3 by 4 product matrix. Okay, but vice versa, if I did matrix B times matrix A, so like I said, order is important with matrix multiplication, then it would be a 2 by 4 times a 3 by 2, the 4 and that 3, so 4 columns on matrix B and 3 rows on matrix A. That is not equal, which means I would not have a resultant product matrix. So I have to have that same number of columns on the first matrix and row on the second matrix to actually get that product to exist. So let's do a couple of practice one real quick. So we're going to do S times P. So S is, and I think it's going to be easiest if we kind of go through and identify all of these first. So P is a 2 by 2. Q is a 2 by 1. R is a 1 by 2. And S is a 2 by 2. Okay, so S times P is going to be a 2 by 2 times a 2 by 2. Note that my column on S is the same as my rows on P. So that means I will have a resultant product matrix, and that product matrix will be a 2 by 2 because it always comes from the rows on the first matrix and the columns on the second matrix for our answer. Okay, then let's check Q times S. So Q is a 2 by 1. And S is a 2 by 2. So note those inner pieces are not equal, which means this one is not going to give us a resultant product matrix C. Okay, go ahead and pause me, do PR and QR for me real quick, and then you can unpause me and check your answers. All right, so P times R is a 2 by 2 times a 1 by 2. Once again, that is going to be no good. So we will not have a product for P times R. And then Q times R, that's a 2 by 1 times a 1 by 2. So that 1 and that 1 are equal, which means we are going to have a product. And that product, remember, always comes from our outside pieces. So it is going to be a 2 by 2 resultant matrix. Okay. So pretty straightforward, hopefully. Now let's actually do the hard part, and let's actually do some matrix multiplication or finding that product of two matrices. Okay, so the reason why we had to have that equal number of rows to columns is because that's how we're actually going to multiply when we're doing that matrix multiplication. So to find that new element in my resultant vector, I'm going to multiply each element in the row of A to the corresponding element in the column of B, and then I'm going to add those pieces together. Now, this is really, really weird to think about, okay, which is why this is kind of our build-up concept. Okay, but we can see right here, so A11 is going to multiply by B11, so first item in first row times first item in first column, and then second item in first row times second item in first column. And then we add those two multiplications together. Okay, and then we just repeat. So then for our next one, it's A11, A12 times B12, B22, then A21, A22 times B11, B21, and A21, A22 times B12, B22. Okay, so we're just doing that same thing to get those four resultant pieces. Now, it's kind of weird to think about when we just see it all symbolically, so let's actually put one into practice. Okay, so if we are multiplying these matrices, if I have the matrix A and matrix B, I want to find A times B. Now, of course, this is a 2 by 2 times a 2 by 2. So those inside pieces, columns and rows are correct from A to B. So we are going to have a resultant vector, and that resultant vector should be a 2 by 2. Okay. So then I'm going to take my first row, okay, in A and multiply it by the first column of B. So 2 times -1 and 1 times 0. 2 times -1, of course, would equal -2. 1 times 0 would equal 0. Then I add those together. -2 plus 0 equals -2. And that gives me my first term of my resultant matrix. Okay, and then I just repeat first row again, but then second column. So 2, 1 times 3 and 4. So 2 times 3 plus 1 times 4. 2 times 3 is 6, plus 1 times 4 is 4. 6 plus 4 would equal 10. Okay, and then second row now, but first column again. So -3, 0 times -1 and 0. So -3 times -1 is 3. 0 times 0 is 0. 3 plus 0 equals 3. And that gives me my next piece. And then last but not least, second row again, but now times fourth column. So -3 times 3 is -9. 0 times 4 is 0. -9 plus 0 is -9. So my product of 2, 1, -3, 0 and -1, 3, 0, 4 is -2, 10, 3, and -9. Now, it can seem a bit weird and seem a bit convoluted. So that's why we're going to do lots of practices this one, because this skill is really what we're going to apply to actually solving our system. So let's look at this first example. So 2, -1, 5, 3 times 0, 4, -3, and 1. Now, quick thing to check. This is a 2 by 2 times a 2 by 2. That 2 and that 2 are equal, which means I am going to have a resultant vector, and that resultant vector, of course, would be equal to a 2 by 2, because that's what my outside pieces are. Okay, so I'm all good to go. I can go ahead and do my multiplication. So what I'm going to do, I'm going to take this first row, and I'm going to multiply it by this first column. We'll use a different color to help everyone out a little bit here. Okay, so 2 times 0, so 2 times 0, and then plus, so second term, so -1, and then times -3. Okay, And that is just going to be my very first term of my resultant vector. Okay, then I'm going to do first row again, but now times my second column. So 2 again, but then this time times 4. And then I'm going to add that to -1. And then this time times 1. And then I just repeat as I go across, but this time I am doing my second row and I'm doing my first column again. So 5 times 0. And I'm going to add that to 3 times -3. And then second row again, but this time second column again. So 5 times 4. And then I'm going to add that to 3 times 1. And then all I'm doing is simplifying as I go across. So 2 times 0 is 0, plus -1 times -3 is 3. 2 times 4 is 8. -1 times 1 is -1. 5 times 0 is 0. 3 times -3 is -9. 5 times 4 is 9. And 3 times 1 is 3. And then simplifying from there, 0 plus 3 is 3, 8 minus 1 is 7, 0 minus 9 is -9, and 9 plus 3 is 12. Okay, so we can see my final answer, I ended up with that 2 by 2 as we identified in the beginning. Okay, so a little crazy, lots of little math, but the big thing with matrix multiplication, y'all, it always follows that same pattern. So just take your time with these. They're going to take a little bit of time. They're going to take a little bit of practice to get good at. Okay, so I want you to go ahead and do that second question. Okay, 2 -1 6 times 2 0 -1 0 6 0. Okay, once again, identify is our product going to actually exist first, and then go ahead and do our multiplication. So go ahead and pause me, and then I'll go over it. All right, and one thing I want to go over real quick on the last one, sometimes I'm a dummy. 5 times 4 is equal to 20, not 9. That's 5 plus 4. 5 times 4 is equal to 20. So we'd get 20 plus 3 on that last term, which would make my bottom right term 23. Okay, so quick correction on that last one. But let's look at this final one. So 2 -1 6 times 2 0 -1 0 and 6 0. That's a 1 by 3 times a 3 by 2. So checking real quick, 3 and 3. So 3 columns and 3 rows, those are going to be identical, which means our product is going to exist, which is perfect. That's what we're looking for. And of course, that outside is going to tell us what our product will look like. So 1 by 2. So it is going to be a 1 row, 2 column product matrix. Okay, super, super simple. So then we are going to take this first row, which is our only row, and we're going to multiply it first by this first column. So 2 times 2 plus -1 times -1 plus 6 times 6. Okay, so that's going to create our first term. Then I'm going to take that first row again, but we're going to multiply it by our second column. So 2 times 0 plus -1 times 0 plus 6 times 0. Now that first set is going to give us 2 times 2, which is 4. -1 times -1, which is 1, and 6 times 6, which is 36. And then our second term, 2 times 0 is 0, -1 times 0 is 0, and 6 times 0 is 0. Then simplifying each of those, 4 plus 1 plus 36 does equal 41. And of course, 0 plus 0 plus 0 does just equal 0. Okay, and that gives us the resultant vector of 41, 0. So a 1 by 2, just like we identified. Okay, so that pretty much wraps up matrix operations, y'all. If there's one big piece, and it kind of combines all of those skills, but matrix multiplication, that's the big skill that we want to pull out of this, because we're going to really apply it next time on 1C.4 when we solve systems using matrices.